Okay, hello, welcome to the, okay, I hear audio. You can't be too sure. I screwed up last time and we spent 5 minutes dicking around with the audio. So, welcome to the, what is this? The Packet Bomb live stream experience, episode 3. Happy Thursday, 6 p.m. Good audio. Yes, thank you. It was really stupid, of course. You know, if you guys, if you've been paying attention, you know that I've got a new PC, so I keep moving it around and shuffling things. I put the mic on here, and when you unplug and replug things, maybe in a different USB port, Windows isn't super smart to like know that it, I don't know. Anyway, I had to retell it which port that the microphone was on, but I couldn't figure that out at the moment. I was too flustered, you guys, stressed. Anyway, it's fine. So Thursday this week, we've got some, this is tequila soda, some mango juice, twist of lime, and some Trader Joe's has this nice chili lime salt that I've got on the rim. So what are you guys sipping? I mean, I know for not everyone it's, you know, it's 6 o'clock. It could be who knows what morning for you. Thanks for spreading the word, Mr. Bruland. I appreciate that. Getting some folks to come check out our study sessions for Wireshark. So it's got to be, you know, there are some good tequilas. I just went, my go-to, you know, that's if I don't want to splurge a bit, my go-to is Casadores. It's like $25 and it's pretty solid, right? I like Casamigos. I think the first one I talked about, the Rocks Terramana, it was good. It was fine. I had the Reposado. But it's too hot. It's too hot. Like I close my window so you don't get too much street noise. But it's hot in San Francisco, so I was going to do bourbon, and we're doing a more of a tropical flavor thing, which is okay. It's the first time I've made it. I did one last night with strawberry. It was really nice. So, what's going on? I got some stats up. I've never watched the stats, like frames dropped and all that. I think it's doing okay, the health of the stream. Got like a little command center on one side of the screen, and then Wireshark on the other side of the screen. Having a good time. So you guys probably know about Sharkfest. I've talked about it. I hope you guys will go one day. I've been wearing a different Sharkfest shirt each video. This one is really probably one of the better ones. I mean, in terms of style, right? It's beautiful. It's an instructor shirt. I don't remember what year. Maybe 2017. But, yeah, we'll talk about Sharkfest some more because there's breaking news if you haven't seen. It's virtual this year. It got canceled. It was going to be in Kansas City in Gerald's hometown, like right about now, I think. I think it was literally going to be this next week. I could be wrong, but it was around this time. It's been canceled for something. I'm not sure what. There's something going on in the world. I'm not sure exactly what it is. Tribbles. So it's moving to October and it is virtual. I'll bring up the website when we switch to the screen mode, just so you'll see. You can go and you can register. I think it's free. Don't quote me, but I think it's free. Glenn Levitt, Modelo, love all those choices. Those are beautiful choices. There are courses that are in the days leading up to Sharkfest. Those will be paid because those are like smaller groups, instructor-led, deep dives, you know, like training classes, not so much as a conference, right? Those you got to pay for. But I think the conference is online. I'm going to present some case studies. I think it's going to be free. Don't quote me on that. So if you guys missed it, I put out a new video. My first video, I'm a little embarrassed to say, I've been distracted, had things to do. An actual Wireshark video, maybe the first one in 4 years. I think the previous one before that was Packet Bob happy little packets. And then I did a wireshark infomercial, which is, there's nothing useful in that. It's just for your entertainment value. And this is the first one that I put out. I was trying to connect this new PC that I talk about to a really old ReadyNAS Netgear. It just gave me a crappy error. So it's a simple fix. It's not a great fix because you have to enable SMB1 on Windows 10. But at least, again, the whole point of my videos is not like, here's the solution, A to B. It's, here's the process that I use to solve it. And that's, to me, I hope that's the value that you get out of what I do. So other things I wanted to mention, I dug out some books that I have. You guys might recognize some of them. This is Stevens Volume 1, TCP Illustrated. I don't know what edition it is. There's some debate around, the various editions and how they're updated. But, it's a good bedtime reading. Of course, this one's heavier. This is Volume 2. You get into like code level stuff. Honestly, I don't think I've spent much time on this one. But I think I bought it. How did I get this? I think I bought it cheap off maybe eBay because it's got a weird sticker on it. Compliments of something marketing. But the first one I would definitely recommend to read. And then I think Chris Sanders presented at Sharkfest, and I think maybe these went out. Oops, sorry. These went out to maybe the instructors. This is covers Wireshark 2.0. It is the 3rd edition, but he puts out good stuff. And the other two I have, I think this one's pretty good. This is Laura's Troubleshooting with Wireshark book. It's not quite the Bible that this one is, and this is an older version. I think this is more like a study guide for the certification. Anyway, these books are collecting dust. Anyway, I thought maybe in a future one, over the next however many, we could do like a giveaway but you have to be present to win, and I don't know exactly how that would work. To randomly select I'll Google it. If you know of a good way to do it, like live, select somebody who's in the chat or watching, that would be cool. Otherwise, we can figure something else out, but that could be fun. Okay, I don't want to spend too much time on the ramble chit chat. Let's go here. So I mentioned Sharkfest. This is a new website, sharkfestvirtual.wireshark.org, where you can go, I guess, and register. If let me know if it's not free, but I think it is. What else? So what we're going to talk about today, ladies and gentlemen, boys and girls, the last couple we've talked about like applications that were broken, right? We talked about, what was the first one? It was streaming, right? It was streaming. See, I've lost all sense of time because every day is the same, like Groundhog Day, and I've lost the ability to tell. Yeah, so it was two vendors, talking to each other, setting up news stories for a television station, and it was broken. And who's at fault, right? That's what we figured out. The second one was Call of Duty, home network. Why is it a disconnect? And we figured that's broken. But then we get to performance, right? Where it's not broken, we're just not getting the expected result that we want. And this is where, to me, so much of the pain lies with finger pointing. Is it the application? Is it the server, the network, the WAN, provider? So many things. And like the network, what does that mean? And the thing that sort of falls in between the cracks is TCP. Well, who owns TCP, right? I mean, that's just something that's riding on the network and its behavior. So if you're strictly a network engineer, network person, you could arguably say, if there's a TCP problem with your application or your server, it's not my problem, right? You could argue that. If you're a server guy, server admin, and you're spinning up servers and installing applications. Do you on TCP if it's not working well? What if it's working locally, but then you migrate to the cloud and now the performance is bad? Is that the application developer? Is that the admin? I don't know. What do you guys think? What is your experience? I think in big companies where there's lots of division of labor and you have teams focused on one thing, firewall team, the network infrastructure team, the performance team, this team, then yeah, I bet it's hard, right, to say who owns what, and there's maybe lots of finger pointing. If you're a smaller shop, right, maybe you own everything. Or maybe my first job was just like the Unix and network guys and the Windows and Novell network guys. That's how long ago that was, right? Those were the two main teams. You had DBAs and whatnot, but those were the two main teams. So we could work together if there were problems. My opinion is it behooves everyone to understand the basics of what is going on in the wire. If you're an application developer, if you're a server guy, if you're a network guy, it helps out so much to understand what's happening and be able to pinpoint the problem and move on. Give it to the right people and stop pointing at each other. Have some data, determine what the problem is, right? And that's why I think this is applicable for anyone, not just network folks, who is usually the people who are going to check this out. So kudos to you, right? Potentially TCP is not your problem, quote, but it helps you to be able to know TCP and be able to say, hey, this is a problem. This is what's going on. So to that end, this could be, a series of live streams or videos or whatever. Maybe it will be. My initial thought was, actually Fidel let me know about an FTP problem that turned out to be, if you upload, it's slow, but you download, it's fast, quote, fast. And he ended up figuring out that it was the receive buffer or the receive window on the server, because normally FTP servers, I guess you think about downloading, but uploading to it was too small. You bump it up, problem solved. It's pretty straightforward, and we could look at that. That's kind of like a 101. Receive window is like a TCP performance 101. But guess what? We're just going to dive right in, and maybe we'll pick apart some of these in future videos. So what this is actually the download that was fast. But is it good enough? I mean, if no one's complaining, I guess it is. So we're not necessarily going to like solve a problem, but we're going to start pulling apart what's actually happening. What is the performance? If someone says, here's a pcap, what is the performance you're getting? Because if you're looking at your FTP client or an application, it's telling you a throughput. That's the application throughput, right? That's not the network throughput. Those are different things. So we're going to look at that. So that's my opinion on why you should learn this stuff. People that just, it's not my problem and push it away. I've run across plenty of people. You've run across plenty of people. Maybe you're one of those people. In my experience, the people who stand out to me, who make an impression on me, who I would hire, are the people who they want to solve the problem because they like solving problems. And that was me, right? If I can solve the problem, I want to solve the problem. I want to be the guy. Give me all the glory. At some point, if I can't, or if I say, hey, this is a problem over there and there's nothing I can do about it, then let's bring those people in or hand it off. But, just pushing it back and forth, I think it's always better just to dive in. Okay, I think what we'll do is we've talked about TCP. I've got some notes. So let's just have a look. So this is a download pcap. I have not put them up to download. I apologize. Maybe I will after the fact. And when it becomes a recording video, I can put it in the description. But these are not my pcaps. I did scramble the IPs. Not that it matters. It's private IPs. And clearly it's just a test FileZilla thing. But I left the data in because these are, I forget how many bytes, 300 megabyte pcap. So it's a little bit slower to filter, and I was going to just cut off the TCP data, but then it limits some of our reporting visibility. So I just left it in, all right? So what is it? What does fast performance look like, right? I mean, ideally, you know what the bandwidth you're working with is. If it's 100 megabits or 500 megabits or 10 megabits, at least ideally you know that. Maybe you don't. So just right off the bat, the overview, the file properties is going to tell you quite a bit about what's going on here. We can see that it's 44 seconds long. We've got almost 400,000 packets. We've got 44 and a half seconds, almost 9,000 packets per second. And if we come down to the bottom, we're getting about 72 megabits per second. Now that's over the entire capture, right? So captured on the left, displayed in the middle. I haven't applied any display filters, but remember that could be useful later. So every packet in here over the entire thing, it's just simple math, right? How many seconds, how many bits, how many bytes, you get 72 megabits on average across it. So, okay, that's not bad, I suppose, depending on what you're dealing with. You can also look at conversations to get a view as well. If we look at TCP, there's only 3. There's 2 port 21, which you probably know is, FTP control port, right? And then there's some random high numbered port with about 400 megabytes. So there's your data transfer. And this tells you for this one TCP connection, right? Again, just the whole thing, TCP connection, we're looking at about 84 megabits per second, right? So that's better than the average of the whole thing, which is, what was it, 72, something like that? So 84 megabits for the one actual download connection. But again, does that count just TCP? I don't know, now that I think about it. If the IP view of it, there's only 2 hosts talking. So we only get one flow here if between these 2 hosts. Yeah, it's different. So this is another way that you can look at. Did Frank teach you all this? Hello, Greg. Greg and I worked together a long time ago. Frank was our awesome boss, RIP. I wish I had known a lot of this back then. It would have been useful, to be honest. But it didn't. I learned. So another place you can look is protocol hierarchy. And I think this one's interesting because you kind of breaks it down for you. So at the frame level, right, all the bits that we can see, we're looking, again, it's 72 megabits, right? That's what we saw. That's what we saw in the summary. That's everything from the frame layer down. If we come down to Ethernet, well, that's just a header, right? A few bytes header. Well, that's right about a meg for that overhead. And then you have IP, and you have the throughput for TCP. Then you have the throughput for TCP data at 68 megabits per second. So you could say that so that's the application throughput, right? You have to think about, again, the different layers in the stack. And then when you're talking about, if you step back big picture and think about network throughput, well, you're probably talking about everything, overhead, everything. How much can I push through this pipe? I don't care what it is. How much can I push? But then when you're talking about application performance, FTP, HTTP, well, the throughput's different, right? Because you have overhead. So in this case, we've got at the TCP layer, there's 2 meg overhead above it. If you come down a layer under TCP to the application protocol, it's 2 more meg. So the TCP headers account for 2 megabits per second of overhead, right? Things to know. So now we kind of have a view of what performance we're seeing. And we still don't know necessarily if it's good or bad. Now, if I didn't know what the bandwidth was of this, but if I knew, let's say it was 100 megabits. Is this good? Well, maybe. What else is happening? Am I the only person talking? Am I at a site with hundreds of users sharing the bandwidth? You know, these are things to think about. Is there QoS in place for this traffic? Now, I want you to gather yourself for a minute. I'm going to do something I don't think I've ever done on a video. Maybe once, maybe one short, tiny video at the very beginning, I use this tool. It's not because it's not a good tool. It's not in my normal workflow. And that's shame on me. IOGraph. I bet you guys use it a ton because it's a good tool, right? So the default view of whatever version I'm using, 3.2.4, is graphing all packets and all TCP errors, or tcp.analysis.flags, right? That's if you click down, and I remember last live stream when I didn't click the button in the lower left corner, and that would have told me the problem with the Call of Duty duplicate IPs right away, and I didn't do that. That's what that is telling you, right? Well, that's expert analysis flags, but this is TCP analysis flags, which is a subset. So strictly about TCP. Analysis flags is things Wireshark wants to tell you about, you know, what it's, if it thinks it sees DUP Acks or retransmissions or things, zero window, things like that. So we clearly see that it starts to ramp up, it drops, and then it shoots way up here, and then it drops off. And then it's like a roller coaster ride. And what do we see in the dips? TCP analysis flags. So that's like super useful. Right away, we know, okay, clearly there is something happening on the network that is impacting our performance. So I think this is useful. If you want to understand the actual throughput, let me turn these off. I already had this before. This is, again, looking at just the data throughput, right? Graphing, and I'm graphing bits. So then you can easily zoom out and you can say, okay, it literally flat tops. I mean, it's going up like a rocket, and then it goes and flattens out right around, I don't know, what is that? 115 to 120, 117-ish. Just flattens out. It stays there for, we can eyeball it about, these are 2-second intervals, you know, about 4 seconds, right? And then it drops off. And we know if I click this and graph it, it won't be helpful because the numbers are too crazy. You can turn it on, but I mean, it's not that useful unless you turn on log scale. And then it really flattens out your graph. But you can kind of see it, right? You can see the little dips, and you can see that those where the errors show up. So from this, it looks to me like, police, we're hitting in the neighborhood of 120 megabits per second is the tippy top. So potentially that's what the throughput is. And then I asked Fidel after the fact, hey, it looks to be about 120 or so. What is he say? Yep, that's it exactly. So this tells you that we are hitting the max, but then we have something happened. We back off, we ramp up, we back off, and then the average becomes around 70 megabits, right? So that's our performance. Am I going to use this again later? I don't remember. I'm going to close it. So there are file properties, conversation, protocol hierarchy, IOGraph. There are 4 ways to look at the performance that you're getting in your pcap. Use your favorite one. So now let's look at some packets. This is thirsty work. So we have three-way handshake. Always, 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 always get the three-way handshake. Why do we want the three-way handshake? One, I like to look at the three-way handshake to see what the round trip is, to see where I'm capturing this from. Did I capture this on the client, on the server, in between? Well, the client on FTP initiates the connection to a FTP server on port 21, which is exactly what we see here, with the syn or synchronize flag set. So if you think about it, oh, I downloaded a tool, look. Send flag Okay, it's not that cool. The client sitting there decides, I'm going to initiate an FTP connection. So at time 0, right, over here at our time offset, time 0, the SYN goes out. Now it has to travel wherever it's going. Could be next door, could be across the world, to the server. The server receives that SYN, and then it immediately, generally, responds with a SYN ACK. And that SYN ACK has to travel back to the client. So if we see a delay between the client and the server, I'm sorry, between the SYN and the SYN ACK, we know that we're capturing on the client. If you see, and then immediately after receiving the, sorry, I should be looking at the delta. Immediately after receiving the SYN ACK, the client completes the three-way handshake with an ACK, and that took, microseconds. If we were capturing on the server side, which I have and we'll probably look at, I should have opened Wireshark for that. The delay is between the SYN ACK and the ACK, because I'm a server. I'm minding my business. People are going to talk to me, but I'm just waiting around for people to talk to me. At time 0, the SYN shows up out of the blue, and I immediately, probably within microseconds, reply with a SYN ACK. Now the SYN ACK is the one that's traveling wherever it's got to go to the client, and the client responds with an ACK, and the ACK has to travel back round trip time. So that's where the delay is. Now, the other reason why it's imperative is that you get information that you don't get otherwise. In the TCP options, we know that the maximum segment size is 1460 bytes. The segment size is the amount of TCP data that can be put into a packet, into a packet frame, IP packet. That probably means with an overhead of IP of 20 bytes and an overhead of, at least overhead of TCP for 20 bytes, that's 40 bytes. So we're looking at an MTU of 1500 bytes for this host on this interface. No op is just like, these things have to byte align, so that's just a space. It's a nothing. Window scale, again, if you want to look at window problems, and the host and most hosts use window scaling, this is the only place it's seen, the one time in the three-way handshake, so that it can multiply by 256 every single receive window that is seen on the wire in this connection after this, right? And SACK permitted, selective acknowledgements are permitted by this host. And the response, same MSS, same window scale, SACK permitted. Okay, so now we know what's going on there. We have a round trip time of 65 milliseconds to our server. And that's one, right? Then we have another one here, 65 milliseconds. It was 4 seconds, 4.5 seconds later. Do we care? Probably not, because this was just logging on and doing nothing. And then we log on again. And yeah, it's 65 milliseconds round trip time. And look, you can also, if I click on a packet, if I go to, where do I go? Sequence ACK analysis. It puts in the initial round trip time seen for this connection. It puts it in, like, I think every packet, every packet. So that's good. But again, it has to see the three-way handshake to figure that out. No, I don't know anything about IPv6. To be honest, Greg, can you please learn, and I'll bring you on as a guest, and we'll talk about IPv6, and you can teach us, because I don't know IPv6, to be honest with you. So that is the round trip time. So then we have, yeah. We log on, we enter passive mode. Here's the command that I'm not going to tell you how this works. You probably know if you don't Google it, how that we use this information to get the IP and the high port number to then connect to, and we're retrieving a test file. Yeah, someone's jumping in about IPv6. So then we have the three-way handshake. We'll just double check. It's still right about 65 milliseconds. And then here comes data. So what we'll do first, and this is sometimes a good idea, is just kind of scroll through and see what we see. human brains, we like to think we're logical and, ruled by ration and logic, and it's just not true. But one thing we are good at is pattern recognition. Our brains are always looking for patterns and trying to fit some experience and some information into something we've already seen. Our brains are natural pattern machines. So I just like to scroll through or click through and just look and see what I'm seeing. Does it all look kind of the same? Pretty much. Scrolling through. Let me actually scroll. It might be faster. I don't think it is. Now we see something's coming up. Oh, there's some stuff that happened. So we know we have something, which from our IOGraph, we kind of knew, right? We'll come back to that. So what we see, we definitely see a pattern here, right? We see this 1460, 1460, 0, 1460, 1460, 0. And what this is FTP data, as it says, data, data, acknowledgement. Data, data, acknowledgement. And that is the typical TCP bulk data transfer behavior. It's right down here on the floor in the Stevens book. TCP will acknowledge every other packet. I think it's supposed to be every other full-size packet, but the TCP stacks might do it slightly differently. But generally, it will acknowledge every other packet. So data ACK is TCP doing what it is supposed to be doing, right? And because this is just a one-way data transfer, I mean, TCP is duplex, but this is a download stream, right? The application is FTP. We have a file of, I think, you know what? It's probably up in the control protocol. It'll probably tell you in here somewhere, like how much data it is. But you can also, again, go back to one of these things, like look at our protocol hierarchy. Unix is every 2 full. Windows will ACK every 2, even if not. There you go. We transferred, around 400 megabytes, right? Is about the size of the file. So let's go to the tool that I do use the most. And because it's stream oriented, where I was going with that. The application has a file of 400 megabytes. It is taking chunks of that data and giving it to the TCP stack and say, here, take care of this. And it might be giving it in small chunks, big chunks. It depends on how the application is written. But let's just say it's giving it in 1 megabyte chunks to TCP. Well, TCP can't send a 1 megabyte packet. It's TCP's job to take a stream of data and break it up into segments, TCP segments, put it on the wire, right? So that's what it's just a stream of data. It's one layer up from TCP. We've got a stream of 400 meg, a stream down, one layer down or up, down. It's breaking it up into these 1460 byte chunks. Now, because this is a stream, it's unidirectional, we're going to look at a stream graph. And so you need to click on a packet that's in the flow of the data. So I'm clicking on a server packet and I'm going statistics, TCP stream graph, TCP trace. Now what we're looking at is simply bytes over time. The x-axis is time, as in seconds. The y-axis is bytes. Well, it's sequence number, but this is how TCP keeps track. Again, stream-oriented data transfer protocol. The sequence number is how it determines where we are. If I've sent 100 bytes, 1,000 bytes, if I need to resend certain chunks of it, the sequence number increases one sequence number for every 1 byte that's sent. It's a 1-to-1 mapping. So basically, sequence number is bytes. So up and to the right is good. That's what we want. We want, as time progresses, we want the counter to go up. The steeper the line, the faster the throughput, right? So generally, you want to see a smooth line going up and to the right. And the slope of the line, right, would be the bandwidth, the throughput. So looking at this, we see a few things, right? We see it start out a certain manner, a little flatter. It ramps up, and then it does the undulating sort of this wavy motion, which is just a different representation than what we already saw with the IOGraph, right? So if it starts to flatten out, that means it's less throughput. And as it ramps up and gets steeper, that's more throughput. So what we can see here is that the throughput goes up and then comes down. It goes up and comes down, which is exactly what we saw in the IOGraph. Let's start at the beginning of the connection. And what we have, really have to zoom in, don't you? Is this the first one? I think this is the first one, first set of packets we see. We zoom in, and these little guys, wait. These little guys are individual packets. Their length represent the amount of data that is in that packet. So if it's a long line, it's a lot of data. If it's a short line, and you have to look at the, look at the y-axis to determine, right? We know these are 1460, right? So that these are individually packets. And when this green line goes up to meet the line at the same level, that means these packets have been ACKed. There's a little bit of a space, 2 more packets come in, and the green line goes up, which means these packets have now been ACKed. So at this point, there's no outstanding data. 4 packets came in, they were all acknowledged. Give me my thing back. Then we zoom out, and there's a big flat spot here. We zoom in, and we see 1, 2, 3, 4, 5, 6, 7, 8, which is double what we had before, right? And you can see the green line going up, meaning all these packets are now acknowledged. And this pattern repeats itself. Another flat spot, which means time passed. How much time is that? From like 0.1 to 0.21 to 0.27 is in maybe about 65 milliseconds. This is round trip time, right? So this is how TCP behaves in the beginning of a connection. You may have heard of slow start. The beginning of a connection, we have something called the congestion window. Or maybe you've heard it called the SYN window. This is what determines how much data can be sent in one go. So at the beginning of a connection, the number may be small. So we're going to send, in this case, it looks like four packets went out the door, right? And then we wait. Oh my gosh, did they make it? I hope they made it. Hope they come home safe, right? And when we get the acknowledgments for those 4, we increase the window, the congestion window, the SYN window. We can send more. And so we're going to, in this case, it doubled, right? You've heard, slow start typically has that kind of behavior. So it increases, for every ACK it gets, it increases the congestion window. We acknowledged 4 segments. We increased it by 4. The behavior, the exact numbers, when you drill into these, it's not always perfect, but that's a guideline, right? The point is, it's going to sort of kind of double each round trip up to a certain point. So you can see that this little area of packets, that was not good. That was not what I wanted. This little area compared to this one is longer. And we go up, and then it's even longer, and it's even longer. So our throughput is increasing with every single round trip. This is normal TCP behavior. We're going to back out. And then something happens right in here, right? We have all these red lines are SACK blocks, meaning we had packet loss. So and the cool thing about this is that you can drill in wherever you click right there, it's going to go in the capture. So let's have a look. So everything was fine, man. We were ramping up slow. We were maybe starting to come out of slow start. And we had a problem. So I generally like to, when I'm looking at TCP, I generally like to have a couple more columns, these guys. But I don't want to crowd the screen too much. These are the sequence numbers. Whoa. Sequence number, next sequence number, ACK number, right? So what we can do is say, all right, we're chugging along. Here's our sequence number 2613. We know we sent 1460 bytes of data. You add that together, you get this next number, 84073, is what we expect to be the next sequence number. If we come down to the next packet it sends, sure enough, it's 4073. The next one we expect to see, 5533. We come to the next packet, sure enough, 5533. The next one we expect to see is 6993, and the next one we see is 8453. That don't match. Previous segment not captured, right? How many packets did we lose? Well, we can do the math. You can subtract this sequence number from what was expected, and you're going to get 1460 times 2, because I did it already. I think I did it on this one. It doesn't matter. But you do that math, divide it by 1460. It's going to tell you how many packets were lost. In one of the cases I looked at, it was 2 packets. We lost 2 packets. So what happens when we lose a packet? So if you look at the acknowledgments, these 2 packets came in, and the client said, okay, here's my ACK number, 1153, which means I've received all the data you've sent me up to and including 1152, and the next sequence number I expect to receive is 1153. What do we get? 1153. All good. We come to this one, 4073. So it's acknowledging all the data up to and including 4072. And the next, so I expect to see 4073 next, and that's what we get. When we come here, again, you see this sort of stair step. This matches this, matches this. This matches, well, this one matches this one, matches this one. So 6993, well, we get 8453. They don't match. So we received a packet, and we immediately ACK and say, no, I want 6993. You know, we were ACKing every other packet. When we get an out of order packet, we will ACK it every single time. We don't delay. So we say, no, I wanted 6993. Now, all those red lines on the graph are called SACK blocks. So we did receive a packet, right? We received this packet. And if you go down here, you can see TCP SACK saying, hey, I received 8453 up through 9913, which exactly matches this one packet here. So we're saying, hey, sender, I need 6993, but I got this one. Well, the next one shows up. Now it's in order relative to the one that was received, right? 9913, we got 9913, but it's still not the one we wanted. So we again say, hey, look, I hate to be annoying, but I actually really want 6993. I don't have that one. But if you look at the ACK, now the SACK block, this is called the right edge. Left edge and right edge. The right edge has now increased to include this one too. This is called selective acknowledgments. So we're saying, hey, yeah, I got that one, but I still need this one. This happens for every single packet. If we scroll through here, right? Did you guys catch something right there? A change in the pattern. Watch. You see that? Again, your eyes will learn to just pick these things up. What changed? This one little thing right here. Well, other than obviously these numbers that are changing, but my eye saw this. That's what my eye was drawn to. We sent a different size packet. We've been sending 1460 this whole time. Now we got 648. Experience tells me this is probably just a push flag. And yes, it is. Meaning it's the end of a buffer. No big deal. We'll file that away, but we're not going to worry about it. So for every packet we get that is not the one we want, we're going to immediately ACK and increase the right edge, saying, hey, I got all these packets. I got all these packets. Eventually, come down. How many do we get? Whoa. 171 duplicate acks, and we get a fast retransmission. There it is, 6993. Hallelujah, hooray, we got the one we wanted, and now we continue on as we were. Why are there so many duplicate acks is a question I hear a lot. To answer this question, I will answer in the form of a monologue from my favorite play. We have to think about perspective. We're capturing from the client, right? So every time packets come in, we react right away. 2 packets come in, send out an ACK. 2 packets come in, send out an ACK. On the server side, we sent some data and we were waiting. If we go back to our graph, let me zoom out. This line of packets all together, guess what? They were all sent at the same time. Boom, this packet train went out the door, it's sent, nothing we can do about it. It's gone. Now it takes, what, half of 65, this round trip time is 65 milliseconds, right? So it's 30-something, 32 and a half milliseconds to go from the sender to the receiver, and these packets start showing up. Well, 1 or 2 got lost along the way. Sorry, the rest of the train cars are coming in. Can't stop it. So as they come in, the behavior of TCP is to ACK every out of order packet. And if we lose 1 or 2, technically, because it's a stream-oriented protocol, right? Every packet after that is technically out of order. Now, what happens is the sender, so these ACKs, so this data comes into the client, and the client starts sending these ACKs back. So it takes a full round trip time for all those ACKs to come back to the sender. Once the sender receives the third duplicate ACK, it will go, oh, we lost a packet. Let me resend the one it wants. And it just resends the 1 packet, right? We can probably even spot it because we know it was lost right here, right? Look, there's a gap. All these guys touch each other. There's a gap right here. So, I mean, we can probably come over here and we'll see it somewhere. There he is. We got it. Okay, so that is the explanation of the retransmits, SACKs, etc. Now, what happened when that happened? You saw how we were increasing every round trip. Every round trip, we're sending more and more packets. Our congestion window, remember, that's something you cannot see a congestion window in the header. It's not even, Wireshark doesn't even like calculate that for you. It's not something that's it's only known like in memory, in state on the sender. There's tools you can use that it'll report it for active TCP connections, but it's not something you can go look for. You just kind of have to count the packets and figure out. Congestion window is usually, it's counted in MSS. So if it's 10, that means 10 MSS, 10 packets. Well, look at what's happening between the round trip times. We're sending less and less packets. That's TCP backing off. It's doing what it's supposed to do. We hit a limit in the network. We drop packets. Well, all right, hold up, back off. Let's slow down. Everyone take a second. How we doing? And we start again. We start increasing the amount of data we're sending per packet until we hit right in here and we really take off. If I had to guess, this is like still sort of like slow start behavior. And there is a certain threshold of congestion window when TCP will switch state and go into, I forget what it's called. Someone probably knows. But now we're just really cranking along, right? So we know another way you can look at, sometimes I look at these and I go, okay, well, what is the throughput? So we hit another one up here, right? We hit another packet loss scenario right here. And sometimes I want to know, well, what was the throughput before we hit that packet loss? Maybe that's informative for us. So what I like to do is zoom in, just somewhere right in before it, click on a packet before the packet loss. Let me be sure. I'll click on that packet. I go to that packet. I get the frame number and I do frame number prepare filter selected. Oops, selected. And because I was at the high end, I'm going to do less than or equal, right? I'm going to go back. And let's just pick a point down here, right, where it looks pretty smooth. This is moving really fast, and we'll click on that. And we go to that packet, and we get the frame number. And we do prepare and this one we're going to do greater than, right? Because we're at the bottom of the range. And now we're only viewing that little segment of packets in that the steepest part of the line. And we can go back to one of our tools, even just like the capture file properties, and we can see the overall throughput. Now, not the application throughput, remember, the overall throughput, all the packet, all the bits and bytes and bubbles, 117 megabits. So if it's a 120 megabit link, right, and we're sharing it with other people and we're maxing it out, yeah, we might have some packet loss. So I want to start to bring this home. We talked about bytes in flight, right? That's the packet train. Bytes go out the door, they're gone, they're in flight, and you can see it in the capture. However, again, this is where your perspective matters. So it is under, I think it's under here too. If we go, yeah, bytes in flight, we will apply as column. Because we're on the receiver side and we're acking as soon as the packets come in every 2, well, we don't get above 2 packets of bytes in flight, right? If we get beyond that, well, then we're falling behind. We're not processing the packets fast enough potentially. If we were to look at this on the server side, we would see the bytes in flight, go up dramatically. Okay. Why don't we look at the server side? We'll wrap this up and look at the server side, which is this one. So as mentioned, this is the SACK through a handshake, and you see that the delta here is between the SACK and the ACK. So we're on the server side. If we scroll down, I'm going to hide these. I don't think we need them. I'll leave them for now. You might notice some differences with this one. Let's put this guy, say, in the center. Maybe it'll make it easier. We don't see 1460 here. We see much larger numbers. So we know that, I mean, is this some kind of crazy jumbo frame? No. This is segmentation offloading, right? Feature is enabled on this host that we're saving CPU cycles to do the actual breaking the stream data into MSSI segments. We're giving that to the NIC. The NIC is doing that for us, and it's going off on the wire. This is why it's important, if you can, to get a span or get a tap, because if you're, in some cases, you're not seeing what's really on the wire. If we go back to for example, sometimes slow start starts with just 1 or 2 segments, but we remember on the client side we saw 4. Well, let's find. So here's the first data packet from the server, and it's 4 MSS. So it sent 1, which then was broken up into 4 on the wire, and it waited a full round trip for the ACK to come in before sending the next one, and it sends 2. And then it waits a round trip. So it's sending 1, wait, 2, wait, but remember, these are 4 MSS each. So it is still doing TCP-like behavior, but honestly, it can be really challenging. Like when you're trying to understand TCP behavior on a host that's using segmentation offload. If we go to, you can also do TCP. People like to do TCP analysis flags, sometimes right off the bat. And look, so this is that first drop we had. Here, I'll just kill the filter. So we sent 32K, another 32K. At this point, we have, 262K bytes in flight, right? Those are packets out the door, waiting to be acknowledged, unacknowledged data. And then these acknowledgements start coming in. And we see, ACK. And again, these are ACKing every 2 packets, right? Because remember, these big boys are broken up into MSS size packets, and the client is ACKing every one. So these ACKs represent 2 MSS sized ACKs, packets, payloads, segments, acronyms, synonyms. And then we see the 6.9, the one we saw on the client side, and then we see the DUP Acks. Now, it's supposed to see 3 of these boys and send the fast retransmission. That's ideal. That's what it's supposed to do. In this case, we saw 5 before the fast retransmission. I mean, they all came in really quick, right? They all came in within microseconds of each other. Sometimes you're just going to see that. Is that a problem? Probably not. I don't think I would spend too much time worrying about it. But the sender goes, oh, I've got multiple DUP Acks, 3, 5, whatever. I need to send this back. I'm not going to wait for the timeout, because every segment that it sends, every data that it sends gets a timer, right? It sets a clock. When that clock expires, if I have not received an acknowledgement in that time, I need to resend it. That's called a timeout. That's usually much further apart. Fast retransmission, we don't wait. Like, oh, you told me something. You told me you lost this. I'm going to send it right away. It's supposed to result in better performance. I have seen this vary based on the stack and operating system. I've heard people say there's no penalty for a fast retransmission. We know that's not true. We saw the data. It was doing this. It dropped every time there was a fast retransmission. That behavior is controlled by the congestion control algorithm on the sender. This is Windows 2012 R2. I think I Googled it and now I don't remember. Maybe you guys know what the default thing is. I looked on this. This is a Windows 10, right? You can run this command net sh int tcp show global, and it gives you a lot of good information. So my initial round trip timeout, which I was just talking about, is 1,000 milliseconds, right? That's how it starts. And there's some stuff in here, I don't know what they are. We could Google them. But there is supplemental, and my congestion control provider is Cubic. There's compound TCP that's, I think, used on Windows servers. There's DC TCP that can be, and there's older versions. I forget what the older one was that would show up here sometimes. But my point is, I have seen, say, Linux, for example, which uses another flavor. The penalty for a fast retransmission is very small. Clearly on this Windows host, it is. So let's go back to the question. Let's wrap this up. Is there a problem? Well, we know that while we're hitting max throughput that we can expect, it's not staying there, and the average is in the neighborhood of 70 megabits per second. Is that acceptable? Is anyone complaining? I don't know. Or, well, I don't know, but is someone complaining? Do we need to look at it? Is the link oversubscribed? Do we have QoS in place? Can we improve it if we wanted to? Well, maybe. Can we use QoS? Can we look for drops in our network? Can we change the congestion control algorithm on the host, right? Because it's working and it's fast compared to the upload. The upload was the problem. It was crawling. No one was complaining about download, but we dug in deep and we found out actually we can improve performance here potentially depending on what the environment is like. I Googled, I thought this was interesting. Where was it? This is from a book, right? This is specifically the version of Windows. And I don't know what this is. I tried to Google it and I didn't find much information, but frankly, I didn't spend a ton of time. Modified fast recovery algorithm. Maybe that's a setting we can turn on that'll help this perform better. I don't know. But now that you know what the issue is, Maybe there's something you can do to address it, or maybe it's just what it is. Okay. So if this was over your head, I would recommend you come to my website, go to read, not over your head, but if you want to start, if you want a more structured approach to this, like, cause this is live, it's all over the place. I have one called Understanding Throughput and TCP Windows. It will take you like through each thing you need to worry about when it comes to performance: the receive window, the send window, congestion window, the send buffer. And then I have a video that walks you through, oh, this is the clown one. Yeah. That will walk you through, that will focus on this stuff. I think different, showing you how each one can affect the throughput. So do that. While you're here, you can get a Wireshark little course emailed to you if you sign up. I will send that to you. There's a lot more we can do with TCP, guys. This is, please let me know, send me an email, jump on Discord if you want. I've got a little Discord server. It's in the description. Since I'm sitting here in front of my computer all day with work, I can usually respond fairly quickly. I'm happy to discuss with you guys more about this stuff. So we are at just over an hour. Let me know what you want to see next time. We can do more TCP. I've got some more, other stuff. I am looking for SMB case studies. If you have SMB questions, problems, performance, let me work with you. I'd like to help you out. Take a look. I'm looking for some SMB case studies to use. So with that said, thank you for joining. I hope everyone has a great rest of your week and weekend. And you know what? We'll see you next time here on the Packabomb live stream experience. I will hang out in the chat and see if I miss any questions, and see you next time.